Hey guys, I hope you can all hear me. Thanks for coming along to today's webinar. We're going to be taking you through a demonstration of Inventor NASTRAN. So I'll start with just a little bit of an introduction. So my name's Ian Cross. I'm a member of the Cross Technology Group staff. We are a reseller based in Australia, providing obviously order software, consultancy, training, and services around the Autodesk products, along with other services for Dell, HP, Microsoft, 3D Connection, and so on. So just a bit of an introduction around NASTRAN. If you are unfamiliar with what NASTRAN is, if you're here to find out a little bit more about it. So NASTRAN is a sort of finite element analysis bit of software that comes embedded into Autodesk Inventor. It is part of your product design and manufacturing collection, so you have it already if you have a PDMC. It's powered by the Autodesk NASTRAN solver and offers sort of simulation capabilities that span across multiple analysis types, such as linear, nonlinear, dynamics, and heat transfer. Okay, so to give you a bit of an example of some of the analysis capabilities, we've got sort of linear statics, we've got buckling, pre-stress static, we've got linear steady state heat transfer. We can do composites, assembly modeling with contacts. We've got thermal stress, nonlinear statics. There's a range of different types of analysis that we can do. And in a moment, I'm going to pass over to Frankie, who's going to take you through the demonstration and show you some of the capabilities of NASTRAN. Just I guess, an offering around the webinar. We do have training on NASTRAN. We have a bunch of advanced Inventor training coming up at the end of October and November. And we've just recently partnered up with 3D Connection. So everybody who enrolls on an advanced Inventor training, whether it's iLogic, CAM, NASTRAN, structural or thermal, will receive a free Space Mouse. If you want to know more about those trainings, please do get in touch. The website's www.crosstechgroup.com.au. Email us at info@crosstech.com.au or training@crosstechgroup.com.au. They're the dates there for the NASTRAN training. So the 22nd and 23rd of November is for the structural, and then the day after, the 24th, is for the thermal training. Okay, that is my little intro over and done with. I am going to pass over to Frankie, who will take you through the introduction.
Yay, thank you, Ian. Okay, I'm going to share my screen. Can you see my screen?
Yep, all good.
Wonderful. Welcome, everyone. Welcome. Thank you for taking the time out today for the webinar. We're going to go through some NASTRAN. So I'm not sure what experience you all have. I'm sure that some of you are seasoned analysts. Some of you might be graduates. I want to show you NASTRAN in the product design and manufacturing collection. Coming from a background of design and analysis myself, the NASTRAN plugin alone is worth the price of the ticket for the PDMC, in my opinion. So I was very, very ecstatic when they included it back in 2016. But enough of that. Let's dive into it. So I've got 3 demos today that I'd like to show you. Firstly, starting with linear static analysis, and then moving on to modal analysis and linear buckling. If you're new to analysis, you might not know what these mean. Don't worry, we'll go over it. It should be all good. So we'll open up the first one. Very, very simple model, this one. So we've got what is essentially a rung. It might be something that is welded onto the wall. I'll just move this. Oops. It's welded onto the wall and somebody steps on it here. So will it plastically deform? Let's find out. So to get into the NASTRAN environment, we can do it directly from inside Inventor. You can come over to Environments, come to NASTRAN, and it brings us into the NASTRAN environment. Does anybody know if it's possible to hide this? Hide floating. There we go. Lovely. Okay, great. So this is the NASTRAN environment. if you're new to it, it might be a little bit overwhelming when it first appears, but I promise you it's easy as a teddy bear. So what we have at the top is the ribbon. And like all things in Autodesk, we generally tend to work from left to right. Here we can create new analyses. Here we can specify materials and idealizations. Here we can put our loads and constraints. Here we've got some mesh controls, and then we can set it to run the analysis. To the left, where the model tree is, we have the analysis tree. So here we've got analysis 1, so linear static. And underneath it, we've got one called model, which you can consider to be like a library. So we'll start off nice and easy by specifying what material this is. So to start, we'll come along to materials. And we are going to specify the material. So in Inventor, you're permitted to select materials, and it will do things like density calculations, even some strength calculations. But here in NASTRAN, we have pretty comprehensive libraries. So everything from metals to plastics to even some composites in there. So for this analysis, we are going to choose mild steel. So steel-mild. And we're presented to begin with a data sheet. So there we've got the mass density. Here we've got Young's modulus, so the stiffness. Here we've got Poisson's ratio, the yield strength, tensile strength, et cetera, et cetera. Depending on the type of material that you're dealing with, this data sheet can change massively. So mild steel, it's isotropic, it's the same in all directions. But if it's, say, for example, a laminate layer, you might specify it in a different way, orthotropic 2D. So we're going to go ahead and we're going to assign it to the solid. So now the solid is mild steel. Very good. All right, next we'll come along and we are going to mesh this up. So, we'll go and do our constraints first. We'll be good. So it may interest us to look at this design in two different scenarios. One where both of these faces are welded, and in another where the top is welded, but the bottom's weld has failed and it's sliding. So we're going to look at how to do that. Here we've got our subcases where we put our loads and constraints, and it's possible to create multiple subcases. So we'll go ahead and we'll create a second subcase. We'll call it subcase 2, bottom foot sliding. And good practice, we'll rename subcase 1, both feet fixed. Lovely. Okay, next we're going to go ahead and we're going to put our constraints. So we'll come to constraints. And the first one's easy. We're going to choose the top face of the top foot. And here we can add a structural constraint. And here we can fix the degrees of freedom. So it's probably intimidating when you first see this dialog, but I promise you it's not. These tick boxes are simply the locked degrees of freedom. So here we've got translation in X, translation in Y, and translation in Z. Rotation in X, rotation in Y, rotation in Z. Because they're all ticked, it means that they're all fixed. They're prevented from moving. And we want to apply this constraint 1 to both the subcases. So we'll select the subcase from this menu here. And we'll call it constraint 1, top leg foot fixed. Lovely, great. Okay, I'm just going to quickly change a setting on my computer so I can do a little indicator by hitting the control button. It's really useful when you're teaching. Garrett, lovely, great, excellent. Ah, fantastic. Okay, so here we've got the constraint and it exists in both the subcases. So in subcase 1, both feet fixed, we concede constraint 1. And in subcase 2, both the bottom foot sliding, we've got the same constraint there. We're going to go ahead and we're going to add a second constraint. And this one we're going to apply just to the bottom foot here. It's going to be constraint 2, bottom foot fixed. Lovely. And there's one more constraint to add, and this will be for subcase 2. In which case, we are going to permit it to translate in the Y direction. So here, we'll select the face, and we're going to unconstrain translation in Y. It's also possible to select a frictionless constraint here. You'll achieve the same, but it's all the same in this case. Lovely. So there we go. We've got our constraints specified for both subcases. Oh, I forgot to rename it. I'll quickly rename it now. Constraint 3, bottom foot sliding. Good stuff, good stuff. Adequately documenting how you do your setup makes troubleshooting later down the track far easier to do. Okay, next what we're going to do is we're going to put a uniformly distributed load of 1300 newtons acting down on the surface. It's going to represent somebody heavy standing on the top of the rung. So here we'll come along with loads, and we'll select this face. And here we can specify what type of load we're applying. We've got many, many different types of loads. We've got forces, moments, distributed loads. We've got bearing loads. We can even enforce a motion. We can say, okay, go down 1 millimeter and tell us the stress. But we'll keep it simple for this introduction and put in a force. Now, we want to put a force of 1,300 newtons acting down in the y direction. So we'll come to force y. Negative 1,300, and make sure that it applies to both subcase 1 and subcase 2. Good stuff. If we click the goggles, we get a preview of how that load is being applied. Because the load vector comes from the surface, it might be a little bit difficult to see the arrow, but using these controls, we can make the arrows larger and more numerous to make them a little bit more easy to visualize. Now just decrease their size because that's obnoxious. Lovely. Okay, so we'll click OK, and we'll say 1,300 newtons down. And click OK. So fantastic. We've got our loads, we've got our constraints. I think we're just about good to go. So finite element analysis, as the name suggests, it involves finite elements. So basically we have a model, we break it into discrete parts, and then we perform analysis on those bits. So if we were to use the generic settings, we could just say, wham, bam, generate mesh. But if you've got an eye for this sort of thing, you'd say, this mesh is pretty rubbish. Generally speaking, the tighter the mesh, as in the finer these finite elements are, the more accurate your results tend to be. I say tend to be, and sometimes and most of the time, because sometimes you get divergence and your stress goes bananas. It's all the fun aspects of learning FEA. So we're going to go ahead and we're going to change our mesh settings. And here we can play around with the settings a little bit. Here we can change the global element size to 3 millimeters and see how that affects the mesh. Oh, it's looking a bit better. Still pretty potato though. We'll go in and we can see some advanced settings. So here we've got some settings such as projecting the mid-side nodes so that it can conform to curved surfaces a little bit better. Here we've got the maximum element growth rate, which will come in a little bit more useful later. We'll click generate mesh and we'll see the magic happening. Oh, that looks much better, much better. Pretty rudimentary to begin with, but that's okay. All right, so we've got our loads, we've got our constraints, we've got our mesh, we've got our materials. Let's ride. So we'll set this to run. It's important to note that when you have multiple subcases in NASTRAN, all of those subcases, the ones that aren't suppressed, will calculate when you hit run. So at the moment, it's doing 2 sets of calculations. So here we go, here we go. Wonderful, NASTRAN solution complete. Okay, so what do we see? What do we see? What we have are results for 2 different subcases. The first subcase, subcase 1, both feet fixed, behaves as you might predict, where the load is uniformly applied to that top surface. And if we click animate, we can see the mode of its shape change. Once it loads. Beautiful. Now, before freaking out, it's important to note that this is an exaggerated plot. It's not actually deforming that much. We don't live in a world of bubblegum, although that would be pretty cool. What we're going to do is just quickly show you the options. And here we can see the deformation. So we can actually change it to the true deformation, which, while more accurate, is probably less interesting to watch. That's the true deformation. You can barely see anything. So we have many, many metrics that we can see. By default, we're looking at the von Mises stress. So the yield strength of this material is 207 megapascals. From this calculation, we can see that the yield strength, that the von Mises stress is 96 megapascals, which is less than 207. So we're not expecting any plastic deformation, with a caveat to be continued. If we look at the second subcase, however, we can see that the stress is a lot larger. That's because the triangle is broken. This is now sliding downwards. I'll turn on deformation so that we can see it. This is now sliding downwards, and that puts a great deal more stress on here. Now, if anyone is familiar with finite element analysis, it's knowing that silly in and putting silly into the calculator gives you silly results. So how do we know we can trust these results? I mentioned earlier that refining the mesh generally means that you get more accurate results. So what we're going to do is a sensitivity study. We're going to refine the mesh in the area to see if we can actually get a more accurate figure for this, because 211 megapascals is very, very close to our 207 megapascal yield strength. So maybe it'll be okay, or maybe it won't be okay. We'll find out. The refinement will tell us. So we'll click return. And let's go along, and we will come, rather than refining the global mesh, we could come along here and we could say 0.0001 and be here all century to calculate, but let's be a little bit more clever about it. We'll come along and we'll do a local mesh refinement. So we'll come here to mesh control. And here we can choose vertices, faces, and edges and do local refinements of the mesh. So I'll come here and I'm going to pick these faces. I could do the same to the bottom, but for the sake of demonstration, we'll just have it on this area of interest. And here we're going to go ahead and we're going to do a local refinement of 0.75. And now here we can toggle on the visibility of elements such as the mesh and the mesh controls and the loads and constraints. I like to turn off mesh controls because I find them obnoxious. So here we go along. We'll go and generate the mesh. And ooh, looking much nicer, much nicer. Okay, so let's go ahead and we'll rerun the calculation. And if you're familiar with this, the finer the mesh, the more calculations it has to do. And so the exponentially more expensive computationally it becomes. I believe the figure was, if you double the elements, you quadruple the calculation time or something like that. Don't quote me, I'm not a mathematician. All right, so here we go. We've got, this time the metric has changed. This time we're looking at displacement. Don't ask me why it changed. We can see that the peak displacement is 0.2 millimeters that occurs at the bottom in subcase 2. Whereas in subcase 1, the displacement is less than 0.001 millimeters. But let's go ahead and change the metric back to von Mises stress. That's the one we were really interested in. Okay. So with the rough mesh, in subcase 1, we had a stress of 98 megapascals, I believe. And now it's 99.5. So it's barely changed. That's good. That's very encouraging. And we'll check it out for subcase 2. And okay. So it has stayed close to its original value, but we can still see that it's suffering from yield. It is good practice, though, to refine it just one more time, just to make sure that your results are okay. So to edit that mesh control, we'll come along to our model tree over here, edit the mesh control, and change it from 0.75 to 0.25. So it'll be nice and very, very fine. And these results, if they're close to the results we got earlier, should be something that we can rely upon. But I'm not going to lie, friends, it looks like it's already failed. So we'll confirm that with this final analysis here. These habits that analysts tend to take on, such as starting off with a rough mesh and gradually refining it in areas of interest, what kinds of mesh to use, what's the most appropriate elements. All of these are, I suppose you could say, software agnostic, whether you're using NASTRAN or whether you're using another company's analysis software. These tend to be habits that you learn being an analyst, and something that we cover during training. So let's have a look at our von Mises stress again. And let's have a look. Okay, so for subcase 1, the stress seems to be 104. Seems to be nice. Seems to converge around the 100 area, which is nicely about half of the yield strength. It will be fine as long as both of these feet are welded. But what happens if the bottom one slips? Let's find out. Oh, friends, catastrophe. We're going to expect plastic deformation in this area. Now, I often get asked, how can we work out what the final shape is going to be? If it plastically deforms, can we predict what the shape is going to end up like? That is possible. It's a nice trick. You need a nonlinear analysis to calculate that, and that would be something that we'd be covering in training. But so that's linear static analysis. It's all pretty straightforward. I told you, don't be thrown off by the user interface. It's a lot friendlier than it looks. Okay, so we're going to go ahead and we'll finish that analysis. And we'll save it. And before continuing, I always reinforce this because we've all lost data in the past. It's very, very important to know where this data gets stored. So here we've got the file rung.ipt. That's the part file. And here we've got a subfolder with the same name. Inside there's a subfolder incad FEA. And here we've got a few files, fno, log, nas, out, and rsf. So these are just given some random string to give it a name. And you can regurgitate this data. You can come along here to NASTRAN and you can say, load results. And here we can go along to the fno file and it will retrieve that data. But super, super important to know that if you don't rename these files, they will just be overridden when you rerun the analysis. If it didn't do that, you might end up with gigabytes and gigabytes of analysis data without realizing it. So it's doing you a favor. But if you want to keep this data, it's good practice to know that you can just rename them and they'll be preserved. So we'll say FEA results 1. And we'll just name all of those files the same thing. And excellent. And if we were to run another analysis, these wouldn't be overwritten. Very, very useful to know. Okie dokie. So we'll save and close that down. Are there any questions so far? Don't be shy. If you've typed something in the chat and I've missed it, it's because I'm terrible at Zoom and I'm sorry for that.
Frankie, there was one question.
Yes.
Can we use convergence settings for refined results?
Absolutely. So do you refer to automatic convergence?
Yeah.
Yes, absolutely. Okay, so funnily enough, NASTRAN, this isn't, I'm going to show you something first that's kind of related, but not answering your question. So I'll just reload those results. I didn't actually get to go through everything that gets shown. Here we go. So deformed. So here we've got stress. We've got, normal stress, principal stress, von Mises stress, etc. Displacement, strain, reaction forces, other. If we come to other, we can see the mesh convergence and the error. But can you automatically converge? You can, and I'll show you that shortly. But there is one more thing I'd like to show you before showing you that. If you come after the analysis is done and come to these constraints, you can right click and come to SPC summation. And here you can get the net force in that constraint, net force and moment to enforce that constraint. Very, very useful for indeterminate structures. Okay, so automatic mesh convergence. Let's have a look. So generally, I try to stay away from this, not because it's bad, but because I'm a bit of a control freak. But here we go. We can come along to convergence settings, and it's off by default. But here you can say include an analysis. And if this is ticked on, it will use this criteria to automatically converge. So I'll just make it a bit draconian. I'll say a stop criteria of 1% and a maximum number of refinements of 10. And we've gotten rid of that mesh control. So we're starting off with our rough mesh and we'll set it to run. I might, to speed this up, I might, actually, no, we'll just let it go. So we'll say run. And here we go. So it's doing the analysis. Actually, I can speed this up a bit by just suppressing the subcase 2. So it's just doing subcase 1's calculation. So what it's going to, oops, cancel, close, generate mesh. Okay, let's try that again. Run. So what it's doing is it's running the analysis, and then it's calculating the peak von Mises stress in it. And then what it's trying to do is refine the mesh in the areas of interest. So say, for example, it calculates peak stress here. It will try and apply a local refinement. And what we should see here on this convergence plot is a nice asymptote towards a static value. Now, if you are a bit ambitious like I am and you set your stop criteria to be 1%, it might not converge so quickly, but we'll see. We'll see. Hopefully the demo ghost doesn't attack me today. Here we go. Nope, it's converged already. That was quick. Good stuff. Stress. And we can see, yeah, it's already gotten there. If we tried it again with a tighter convergence settings, and here we go. Actually, no, 5. Oh, local refinement, good. Hopefully we can actually see it in action, because I think it converged too well. And away it goes. And it's going again. So from our manual convergence, from our manual refinements, we calculated to be something like 100 or 104 or something like that. So automatic convergence should approach that. Still going. So we've got our convergence rate at the bottom. There's 9.47%. Hopefully the next step will do a bit better. And it's going, it's going. $102 with a convergence rate of 3%. And as you can see, it'll keep on refining it until it gets in or reaches its 10-step limit. I might let it go for another minute, and if it doesn't converge quickly, then we'll move on to the next one. There we go. We're getting a nice asymptote, and it's approaching our 104 manual convergence. Friends, I think I might have been a bit too ambitious for this one. I might kill it after this step. While that calculates, are there any other questions for this first exercise? Ian?
No, there's nothing in the chat windows.
Okay, good stuff, good stuff. Okay. Oh, it's so close. It's got an error rate of 0.2% and 0.21%, and our cutoff was 0.2. I might stop it now, but you get the idea. Eventually, it will just keep on refining the mesh until it approaches the true value. I might stop it after this mesh today. Okay. Have mercy, Nastran. eventually. Here we go. I'll stop it. And there's our nice asymptote. It's approaching our 104 value earlier with the local mesh refinements being applied. Good, good, good. Okay, I'll finish that and I'll close it down. And we'll go on to the next exercise. So the next one is going to be a modal analysis. So we've got here, it's a pinned bracket. It's more just to show off some of the pin constraints and some bearing loads as well, but also the different failure modes. So for this design, it has to have a safety factor of at least 3. It's going to be pulled with a bearing load of 5,000 newtons acting in the X direction. But very, very importantly, it's not allowed to have a natural frequency below 300 hertz. It might be loaded onto some vibrating engine, and it needs to be able to not shake itself to pieces. So let's go ahead and we're going to do a quick analysis. So we'll say environments, NASTRAN, and we'll start off with a linear static analysis. So as before, here we go. We've already got a material assigned. So if a part has a material assigned in Inventor, it will automatically be inherited when you bring it into NASTRAN. As before, what we're going to do is we're going to apply our constraints. So here, come to structural constraints, and we're going to change it to pin. And we'll choose this upper pin. And here we can choose what degrees of freedom are being locked. So we've got our radial direction, so translating, our axial direction, so translating axially, and then tangential direction, which is rotating. Typically, pin constraints tend to not have their tangential direction fixed. We'll make a pin constraint there and a pin constraint there. And here we've got 2 pin constraints that keep it in place. Next, what we're going to do is we're going to apply 2 things. We're going to apply gravity, and we're also going to apply a bearing load pulling in the X direction. So here we'll come along to loads, and we'll apply gravity first. We'll come along and change the load from force to gravity. And here, using X, Y, and Z components, we can change the direction. However, if you don't want to do X, Y, and Z components, you can also say normal to surface. Pick a perpendicular surface. Here we go. Clear it. Oh, it's not cooperating. That's okay. Components, and then -9810. So that's 9.81 meters a second squared acting in the Y direction downwards. So when you click it on, you'll get a neat little icon in the corner that says gravity is on. Don't be tricked because that arrow will always face down, but it doesn't move around with your Y-axis. So always make sure that gravity is acting in the direction you intend. The second load is going to be a bearing load of 5,000 newtons. Now, you might be tempted and might be forgiven for coming along and saying, here, let's go ahead and put loads, put a load acting on the surface, and we'll say, 5,000 in the X direction. But if you do that, the load will be uniformly applied to the entire inside of the surface, which is fine if it's glued in there or if it's, bonded in some way. But in this case, it's going to be a pole that's stuck in there applying a bearing load. So we'll have a look using this little icon, what those loads look like. I'll just increase the density of these arrow vectors. And as we can see, by default, it's applying the load uniformly on that surface. Now, what we want to do is we want to change it to bearing load. And bearing loads have 2 expressions. Here, we've got it applied as a sinusoidal distribution of pressure. But if you want to make it a little bit more rigid, what you can do is change the direction to components, in which case it's just acting normal to that surface at all points. This one's a little bit harsher to the material, but I find it's better if you're using a rough mesh. For reasons that are interesting and have to do with the asymmetries in a mesh. But here we go. So we've got a 5,000 Newton bearing load acting on that surface. We've got gravity acting down. We've got our constraints here. Next, we'll come along and we'll do a mesh. So we'll come along and change the mesh settings to 2 millimeters and click generate mesh. And it's looking pretty good, pretty rough around the edge. That's okay. Again, we can come along here to settings, project the mid-side nodes, generate the mesh, and looking pretty good. So from our design, we were required to provide a safety factor of at least 3. So let's do it. While that calculates, the safety factor is the yield strength of the material divided by the von Mises stress. Well, generally speaking, the von Mises stress of the material. So in a isometric thing, isotropic material. So what we've got is a calculation, and we're expecting the stress to be less than 275 megapascals, which is the yield strength of aluminium 6061. So here we go. We've got 93 megapascals. Here we can see the mode of the load acting on it, as you can expect. We never specified that that circle has to be kept rigid, and so it deforms in hoop mode. Here we go. Yeah, looking good. So we can see that the peak stress is around 90. Now, you could calculate the safety factor yourself, but it's much more convenient to come here and double click safety factor. And here we can see safety factor of 4.3, looking pretty good. Now, as I mentioned earlier, it's always good practice to make sure that you check your results using some mesh refinements. So we'll come along here and apply a mesh refinement to this. And we're not going to spend too much time on it. We did cover it last time. So we'll put a mesh refinement of 0.5 millimeters on these faces, generate, and see if our results are still somewhat the same. As long as the the safety factor is above 3, we'll be satisfied. So it'll calculate. And it should just take a moment. And away we go. Okay, so there we've got 120 peak 120 megapascals peak stress. And if we go to safety factor, oops. If we go to safety factor, we can see, it's just on the cusp there. 3, safety factor of 3. We'll give it a pass. We'll give it a pass. So the other design requirement was that this thing was not allowed to have a natural frequency below 300 hertz. So let's calculate it. We'll go along here, we'll edit the linear static analysis, and we'll change the analysis type. So by default, here we've got linear static, but we've also got normal modes, linear buckling, pre-stress static, non-linear static, even some dynamic stuff, transient responses, fatigue analysis, so we can work out how many cycles this thing can endure before failure, et cetera, et cetera. This NASTRAN is the real deal. It's very, very heavily used in the aerospace industry, and some automotives use it. And so while it is easy to approach and easy to learn, there's some incredible depth here. We'll come along and we're going to go to normal modes, and we're going to calculate the first few sets of natural frequencies. So here we've got modal setup, and we can tell it, okay, go ahead and give us the first 8 natural frequencies of this design. We'll come along and we'll click run, and oops. You'll be very, very pleased to know that the stop button in NASTRAN is one of the few buttons in all of Windows that actually stops whatever you're trying to stop. Lovely, especially when your calculations can sometimes take hours. We're going to delete that mesh control just to speed things up a little bit. Not that it's going to affect the modal analysis all too much. Okay, so it's running, it's doing magic. What it's doing is calculating the first 8 natural frequencies. So that is the frequencies at which you vibrate it, which will build up energy and start to cause problems, particularly fatigue and welds. So it's calculating, it's calculating. It shouldn't take too long. Eventually, you start to become like somebody watching the Matrix code coming down, and you can tell when it's nearly finished. There we go. It's nearly finished. Almost. There we go. Done. Okay. So in this case, in the case of modal analysis, we're interested in two things. So what we have here are the eigenvectors. So we'll say, here we go, we've got mode 1. Its natural frequency occurs at around 293 hertz. Mode 2 occurs at 1048 hertz. Mode 3 at 2200 hertz. So we can come along to one of these modes and we can say, we'll click that mode. And if you click animate, you'll get in mode shape. We'll quickly just change in a setting so that we get the full, there we go, mode shape. And we can see how the design is vibrating over time. This can give you a hint as to how you can reinforce it. Sometimes it's adding in a rib, or sometimes it's thickening one of the members. We'll come along here and there we go. We can see that it's swaying side to side as you would anticipate. Lovely. So how could you quickly iterate this design so that its natural frequency, well, I said that it was meant to be below 300 and it totally is, but say that we want to stiffen it up, make it above 330. We could come along here, we could edit the design. We might change this from 4 to 6 millimeters so that this middle flange is a bit thicker. Come along to NASTRAN. And I'm just going to speed things up a little bit by editing it so that it's only calculated in the first mode shape. We can generate the mesh. And a lovely quality about NASTRAN and Inventor is that you can make a quick change to the geometry, and it remembers where you put your constraints, where you put your loads, where you put your mesh refinements, etc. So it should be very quick to calculate, and hopefully it will bring up the first natural frequency a little bit. Here we go, calculating. Should be close. Just another moment. An interesting thing with modal analysis is that the loads don't actually affect the natural frequencies. They're a property of the structure. There we go. And now we can see, yep, perfect. The first natural frequency occurs at 516 hertz. So it's been stiffened up quite a bit just by changing one parameter that governs the thickness. Beautiful, excellent. Okay, so I'm conscious we're running out of time, so go ahead and save that. Any questions on modal analysis? Ian, in the chat?
Nope, we've got nothing come through so far.
Lovely, excellent. Cool. Okay, so demo 3, linear buckling. So this one is a little bit of a fudge. You'll have to forgive me. So here we've got a design that's not great. It's actually an assembly. You can do NASTRAN analyses on assemblies. You can assign different materials to different parts and whatnot, but I'm going to show you something cooler in this one. So here what we've got are fixtures on the wall that hold up this crucible. This crucible is about 35 kilograms, and it is held up by this very flimsy looking bracket. So what we want to know is, will it yield? But say that somebody's already done the analysis, and I know it doesn't look it, but yeah, okay, it's within the strength of the material to not yield. It bows a little bit because there's quite a bit of deflection because it's a bit skinny, but can it fail in any other way? If anyone's done a few analyses in the past, you might say, okay, something doesn't yield, but that doesn't mean it's okay. In this case, it might be subject to buckling. So that is to say, it might literally kink in on itself and fail by rapid buckling. So I'm delighted to say it's easy to do buckling analyses in NASTRAN. We'll come along to environments and NASTRAN. Now, as I mentioned, it is possible to do the analysis on assemblies. So you can assign different materials, different parts, apply gravity, and it will act in the way that you'd predict. But if you want to reduce the amount of calculation that's required, if you want to reduce the complexity of the analysis, it's possible to use some stand-in tools. So what we're going to create in this case is two things. The first one is a concentrated mass, and the second thing is a connector. So a concentrated mass is an arbitrary point which you can assign a mass to. So to do that, we'll come along to model, find concentrated masses under idealizations, click new. And here we're going to click this point in the middle of our crucible holder. And here we go. We can come along and we can give it a mass. Now, don't ask me why, but for some reason, the mass by default is in tons instead of kilograms. The strangest choice, but that's okay. Well, we said that the crucible and the material in it was about 35 kilograms. So we'll say 0.035 tons. Beautiful. If you have a shape that's not central, I assume that the center of gravity is that point, but if it's not, you can put in your own inertia, moments of inertia. And if you want, you can also offset from that point. So say, for example, if it was offset, in the Z direction by, 10 millimeters or whatever, or 50 millimeters, so you can see, you can change that position. So here we go. We'll just say that's the center of gravity, looking good. Excellent. Click OK. So at the moment, we've got an infinitely small point that has a mass. We need to connect it to our design. So here's where connectors step in. Connectors are really interesting. You can create rods and cables and springs. In this case, we're going to create a rigid body. It's a little bit of a fudge because technically what I'm about to do isn't rigid. But here we're going along. We'll say we want to tie this face here to this point here. Now, keeping it as it is would keep this face perfectly rigid relative to that point. So if the point translates, this face will translate perfectly with it. In this case, is probably an acceptable condition to put, but you can change the type here to interpolation, which allows some flex in that surface. So here we go. Come along and click OK. So now we've got point mass. We've got it tied to the top face of our crucible holder. Now let's put in some loads and constraints. For our constraints, it's going to be easy. We'll pick the back ends of these two blocks. Oops. The back end of these two blocks. And for our loads, we're not going to put any force calculation. We could put a load acting down on this face to represent the crucible, but let's be cool about it and put in gravity. Now, gravity will act not only on the structure itself, but also on that point mass. And when it acts on that point mass, it'll impart a load onto that surface, and then the whole thing will flex. Look like okay. Now, we're going to generate a pretty potato mesh just to speed things up. Ooh, looking garbage. And I'm going to save us the embarrassment of doing a linear static analysis because I did it earlier and it actually does yield, but take it on faith that this design didn't yield. It's magical material. We'll come along and we'll edit the analysis and we're going to change it to linear buckling. Now, the important thing about linear buckling is that it solves a problem that's not picked up by FEA immediately in a linear static analysis. Say that, for example, you had a pillar and you were to apply a massive load to that pillar, that pole, it would say, okay, it's not yielding, but it might buckle very, very quickly. And that's what this analysis will tell us. So we've got linear buckling, we've got our mesh, we've got our loads, constraints, we've got our material selected, concentrated mass. Great. Go ahead and we'll click run. And what it's going off now and doing, it's going to give us some crazy values, but that doesn't matter. What we care about in this case is the eigenvalue, which is basically, you can consider the structural stability of it under load. A good practice would be to actually calculate a few of these for given modes, but for the sake of exercise, we'll just calculate one. It's doing that now. It shouldn't take too long. NASTRAN solution complete. And when it comes to the analysis, we can, excellent. We can load, we can ignore all of these values for stress and whatnot. They don't mean much. This is the value we care about. Oh, eigenvalue of -4. Interesting. Let's go ahead and we will change it to, where are we? Linear buckling, options, number of modes, we'll say 4. So when and this is actually a good opportunity for learning. If you're confronted with negative value. What you're looking for is the lowest eigenvalue in absolute terms. So the lowest absolute eigenvalue is the one that we are interested in for buckling. So say, for example, you got eigenvalue of negative 0.7 and 8 and 4 and 6. The one that you care about is the 0.7. Interesting, interesting. I might have made a small mistake. Gravity acting down. Oh, I guess it doesn't yield. I think I'd reinforced it before the calculation began. Let me check the model real quick. Well, interestingly enough, that eigenvalue of 4 means that it doesn't yield. That doesn't buckle, which is good, I guess, for this design. But let us make it buckle. Where is the sketch for sweet? That's one. Oh, we've got some questions in the chat. Oh, the stress value gets higher. Can you tell the reason for the modal analysis? Right. So for the modal analysis, you can completely ignore the stress values. When something hits its natural frequency, so say, for example, this crucible holder was bobbing up and down. If it doesn't dissipate energy, that is to say, if the material doesn't heat up and it doesn't let out sound waves, it will just keep on building up energy, keep on building up energy. If you can imagine it, you're holding a metal ruler and you're wobbling it up and down. If it doesn't get rid of energy, that energy will just keep on building up. So technically the stress will just keep on building up until the material breaks. So in modal analysis, you can completely stop it. Can you spend another 2 minutes on idealizations and how they might be implemented in different scenarios? Absolutely, absolutely. I'll just set this last one to run and then we'll break from form and we'll do a look at idealizations. We can even use that assembly to have a look. Hide floating things. I'm beginning to think that this thing's not going to buckle, but that's okay. Take care. Lovely. This thing doesn't buckle. Wonderful. So as long as the eigenvalue in absolute terms is above 1, the thing won't buckle. Good. We know. Wonderful. Okay. So I'll go back, running a little bit low on time, but I'll talk about idealizations very quickly. So far, when we've dealt with models in NASTRAN, they've all been 3D models. Now, what is an idealization, you ask? I'll go ahead and create them from scratch. I'll just delete the 2 idealizations that got created here. So at the moment, we have no idealizations in this assembly. So if you click generate mesh, nothing happens because only idealizations get meshed. So here, if we come to idealizations, here we can create our own. So we can say idealization, and we might say a solid 1 bracket. And for the associated geometry, pick this bracket here. Now I'll click OK and I'll return to it and click generate mesh. And there we go. It's generated a mesh for the bracket, but not for the crucible. That's because there's only one idealization here and it includes the bracket. Now, an idealization is a grouping of element types, material, and geometry. So I'll say that again. An idealization is a grouping of element types, material, and geometry. So here I might say, okay, yep, that bracket is mild steel. So I've created an idealization just for that bracket. The second one, idealizations. Here I can say associated geometry, pick the crucible, change the color of the mesh, and say that its material is cast steel. So because they are, they're the, different geometries, different materials, but the same element types, they're different idealizations. So click generate mesh. And now we can see that we've got, there we go, a mesh for the crucible and a mesh for the bracket. So that's the first part. Those are solid idealizations. Would you like to learn a little bit more about the shell elements and line elements? It'll just take a moment if we might overrun just a little bit, but if you're keen. I have lost my bar. Ian, can you read it for me?
For the chart, when the eigenvalue is above 1, does it mean that the model will not buckle?
Yes, that's right. So when the eigenvalue in a buckling analysis, if the absolute value of the eigenvalue is above 1, it won't buckle. So that is to say, if you get, say, -3, it's still in absolute terms above 1, and therefore you're okay. If you get an eigenvalue of, say, 0.7, then it's going to buckle, and you have to worry. Okay. All right. So those were solid idealizations. I'll quickly chat about shells. So shells are very, very useful. I'll just quickly whack up a shell. It'll take 2 moments. Ian, while I do this, could you kindly read out the questions for me?
There are no other questions.
Lovely. Don't be shy. I love this stuff. So here we go. So say, for example, we've got this material. It's a shell. So I'll go ahead and come to NASTRAN and say that we want to do a calculation on this. Say that we want to put a load on here. We could come along here and generate a mesh, but we start to get a lack of fidelity. Because it's very long and very thin, we need a lot of elements to properly capture the cross-section. So typically you want at least 3 or 4 elements, width-wise here to properly capture this. So you might come along here, and if you had the computational power, you could say 0.5 mils, and you might make a mesh that's fine enough to do it, but it starts to become very computationally expensive to do it. So it's possible to, instead of using a solid, using a shell instead. And the way that that works, I'll come along and I'll delete that solid. There we go. Come to a new kind of idealization. And here I'll change the elements from solid to shell. And for the associated geometry, I'll pick these outer surfaces. For the thickness, I'll put 1 millimeter. And for the advanced options, I'm going to offset it so that it's facing, it's going off in one direction. So when you click generate mesh, what you'll get initially is something that looks pretty good. Oh, very nice, you'll say. It's a shell, but you look to the other side, oh, it's gone. So what this is, I'll disable the visibility of the model, so of the CAD body, and that's what we're actually dealing with. It's a 2D shell. Now, why might anyone want to do that? Because it's a lot quicker to do a calculation on the shell than it is to do it using the solid elements. These are extremely, extremely useful. If you had an infinitely powerful computer, sure, you could make solid meshes from everything. But if you're within the mortal realm, then shells are useful. One more very, very important thing before we wrap up. Shells sometimes get misused because how do we know what direction the shell is going in? I'll put it back to its default. So we'll say advanced options, no midplane. We might say, shell's looking pretty good. But if we were to come along here, and if you're taking down notes, I'd strongly recommend taking this one down. Coming to elements, here you can display the cross-section of shells. And I'll toggle that on and off a few times so you can see. As you can see, the shell that we specified is the mid-plane of a 1 millimeter shell. So to correct that, we'll come to our shell. We'll go to advanced options, and we'll change, we'll put in a mid-plane offset. And hopefully, no, it always goes in the wrong direction first. That's how you know you're cursed. We'll come along, change it to -0.5, which is half the thickness, and that's better. That shell is representative of our part and is insanely quick to calculate. Does that answer your question? Learn a little bit about idealizations? Thank you very much. So did you enjoy the presentation? It's a joy when you learn the tools. It's not as intimidating as it first looks. I'm afraid that's all we have time for. So any last questions? No? Thank you very much, Joe. Really appreciate it. It made my night. Okay, I'll pass you back to Ian. Thank you very much for your attention, everyone. You've been great. Really appreciate it. Bye.
Thanks, Frankie. And just to recap, we do have some training for NASTRAN coming up. Oh, there we go. Some training for NASTRAN coming up next month. And 22nd, 23rd November for structural, 24th for thermal. And just a reminder that all of the advanced training we're doing through October and November for Inventor, you do get a free Space Mouse to celebrate our new partnership with 3D Connection. All right, so I hope you guys enjoyed the webinar. Thanks for coming along. If you've got any questions, please do contact us on the details on the screen. Thank you again, and I hope to speak to you soon. Thanks, everyone. Goodbye.
Thanks, everyone. Bye.